All right, let's get right into it. Today, we're going to break down the one core principle that powers pretty much every major AI system you use. We're talking fraud detection, your Netflix recommendations, you name it. It all kicks off with this one incredibly powerful idea: supervised learning. The entire tech world is just buzzing right now. And according to the latest State of AI report, we are officially past the point of just showing off cool demos. 2025 is the year of action. It's all about building real, solid AI systems that make a huge difference. But to build anything that lasts, you need a rock-solid foundation. And that's exactly what we're talking about today. So that begs the question, right? With all this talk about building these smart, agentic systems, what's actually making it all work? What's the academic bedrock that makes it all possible? What's the one thing you absolutely have to get to really understand modern AI? Well, the answer is supervised learning. I want you to think of it like the engine inside a high-performance car. It's that powerful, foundational piece of the puzzle where everything truly begins. So what is it exactly? Well, in supervised learning, you basically give a machine learning model a giant data set that already has all the correct answers labeled. It's kind of like giving a student a huge stack of practice tests that already have the answer key. The model just churns through all those examples, learning the patterns, so that when you give it a new problem it's never seen before, it can make a really good guess. And I want to be clear, this isn't some niche, abstract concept. This is the core curriculum. I mean, if you were to sign up for an AI program at a top university like Berkeley or Stanford right now, these are the exact things you'd be studying. This is the absolute essential toolkit for anyone who's serious about building in this space. And when you strip it all down, supervised learning is really about doing one of two things. On one side, you have regression, which is all about predicting a number. And on the other side, you have classification, which is about sticking a label on something. Let's dig into both of those. Okay, first up is regression. This is the tool you pull out when the answer you're looking for is a number, a continuous value. Think things like quantities, prices, temperatures, that sort of thing. The classic starting point here, the one everyone learns first, is linear regression. It just helps us find a straight-line relationship in data to predict a number. Now, there's a slightly tricky one called logistic regression. And what's funny is despite having regression in its name, it's actually our first step into the other pillar, classification. It's designed to predict a simple yes or no outcome, like, is this customer going to leave or not? It's a bit of a naming quirk, but it's an incredibly useful tool. And here's a perfect real-world example of regression. A model can look at features of a house, its square footage, where it is, how many bedrooms, and after learning from thousands of past sales, it can predict a very specific number, the final sale price. Okay, let's jump over to that second pillar, classification. This is what we use when the answer isn't a number, but a specific, distinct category. Is it A or is it B? A couple of key algorithms to know here are decision trees and support vector machines. Decision trees are awesome because they're so easy to understand. They work just like a flowchart, so you can literally follow the path and see the logic. Then you've got things like support vector machines, or SVMs, which are a bit more of a black box, but they are incredibly powerful at finding really complex, subtle patterns that separate different categories in your data. A perfect high-stakes example of this is fraud detection. Every single time you swipe your credit card, a classification model is analyzing that transaction in a split second. It looks at the patterns in your spending history and immediately slaps a label on it, authorized or fraudulent. This is supervised learning protecting millions of us every single second of the day. Okay, so we've got regression models and we've got classification models. But here's the thing. In the real world, data scientists almost never just pick one model and call it a day. The real magic happens when you combine them into something called an ensemble. The logic here is actually super simple, but it's incredibly powerful. It's basically the wisdom of the crowd idea. Ensemble methods, like the famous XGBoost algorithm, take a whole bunch of simpler, weaker models and let them all vote on the final answer. And that final consensus prediction is almost always way more accurate than what any single one of those models could have come up with on its own. So here's a really crucial takeaway. While you hear all the hype about deep learning and neural networks, for a ton of common business problems that use structured spreadsheet-like data, think predicting which customers are about to cancel their subscription, a well-tuned ensemble model like XGBoost will often get you better results and faster. Okay, so we've gone through all this work, we've built a model, but how do we actually know if it's any good? I mean, building the model is really only half the battle. The other absolutely critical half is checking its work and evaluating its performance.
And to do that, we use a standard set of metrics. Accuracy is the easy one. What percentage of the time did the model get it right? But we often have to dig a lot deeper. Precision asks, of all the times we predicted yes, how many times were we actually correct? And then recall asks a totally different question. Of all the actual yes cases that were out there, how many did our model manage to find? Getting the balance right between those two is everything.
And this is where it gets really important, because the best metric completely depends on what you're trying to do. In a high-stakes field like medical diagnosis, simple accuracy just doesn't cut it. You have to ask yourself, what's worse? A false positive, where you tell a healthy person they might be sick, or a false negative, where you miss a diagnosis and tell a sick person they're fine? You absolutely positively cannot afford to miss a critical case. So in that scenario, you would tune your model for super high recall to make sure you catch as many true cases as humanly possible. So there you have it. That's the foundational engine of modern AI, from labeled data through regression and classification and all the way to evaluation. This is the bedrock that everything else is built on top of. So the big question now becomes, how do we take these powerful fundamental principles and use them to build that next generation of truly intelligent systems that are going to define our future? Well, understanding this stuff right here is the absolute first step.